So when dealing with polarity, the big thing that we have to talk about is nonpolar covalent versus polar covalent. So when we look at nonpolar covalent bonds, we know that our electrons in this case are actually going to be shared equally between the two elements involved in the bonding. This means that they have the same electronegativity, which also means that the difference, if you subtract them, would be that of 0. When we look at polar covalent bonds, the big part here is that we know their electrons are shared unequally. This is what causes those poles to form. So therefore we have the slightly positive and negative ends. So we have the positive end, we have our negative end because of this difference in electronegativity. So we know that there is indeed a different electronegativity from the two of these. When we're looking at that, we know that based off from the difference in electronegativity, you can have some different shapes. Dealing with polarity, we talked about molecular shapes. So based off from molecular shapes, we're looking at our substituents. We know tetrahedrals have 4 shared pairs of electrons and 0 unshared pairs of electrons. Tetrahedral is an example of that. That's most commonly used by reagents is CH4. Second type that we have here is a linear molecule. Linear can be polar or nonpolar, depending on the substituents or the branches off of there. Okay, we also have diatomics, elements that are linear as well. So depending on if there's a difference between the substituent and that of the central atom, depends on if it's going to be polar or nonpolar. If both substituents are the same, in this case maybe like CO2, which is the most commonly used by New York State, we can see that the 2 oxygens would cancel out with one another, causing this overall molecule to be nonpolar. When we're looking at pyramidal things, we know pyramidal are always polar. Okay, the reason behind that is that we have 3 shared pairs of electrons, but we have that 1 unshared pair of electrons, thus causing our substituents to all be different. And since they are all different, we know that it's always going to be polar. The most common use for that is NH3 by New York State. When we look at trigonal planar can be polar or nonpolar. Okay, so if we look at those again, saying if your substituents are the same, then you know it's going to be nonpolar, but if you have a difference in substituents, those outside elements, then we know it can be indeed polar. Biggest part about this is that we have 3 shared pairs of electrons, and the most common example from New York State is BF3. If F's are all the same, then you know indeed that this is going to be nonpolar, but if there was one substituent that's not fluorine, so maybe chlorine, then you would have a overall polar molecule. Just to review for the tetrahedral, remember we have 4 shared pairs, 0 unshared. As long as all the substituents are the same, you're going to be considered nonpolar, so you can be nonpolar, or you can be actually a polar molecule if those substituents aren't the same. Last type we have here is bent molecule. You have 2 lone pairs of electrons, so unshared pairs, along with 2 shared pairs. Okay, and this is what causes this to be a bent molecule. The most commonly used example for this is H2O. So if we continue on here, we're going to look at a couple sample problems. It says, which of the following has a polar bond but is a nonpolar molecule? So we're looking for a difference in electronegativity, but all substituents to be the same. If we look at N2, we know that this is going to be nonpolar molecule and nonpolarly bonded, because the difference between N and N would be the net 0. H2O, we know H2O is actually a polar molecule due to the double lone pair on the oxygen. We have NH3, which we know is also going to be a polar molecule because of the lone pair on the nitrogen. And our last piece here we know is CCl4, which we know to be that of nonpolar because all substituents are indeed the same. For the following, I want you to draw Lewis dot diagrams, including unshared electrons, identifying the shape and determining the polarity. So when you're looking at the following here, we know that we have oxygen. And we know that the oxygen, based off from here, is going to have 6 valence electrons because it is found in group 16. So as I switch over here to the marker, we can see that oxygen, so we're going to have our oxygen here, sharing 2 pairs of electrons to the other oxygen. It is our only diatomic molecule that actually occurs with a double bond in the center. So we have our double lone pair giving us 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Shape being that of a line. And we know that this is going to be nonpolar because the difference in electronegativity is that of 0. When we look at HBr, we have H here. Okay, so looking at H is going to be single bonded to Br. Br has 7 valence electrons. Since it has those 7 valence electrons, it picks up that extra shared one from the hydrogen, thus giving us 8 valence electrons. Shape here is also going to be linear. And our polarity is going to be that of polar. Next part here we have is BF3, one of our examples that we used just before this. And when we're looking at BF3, we know all our substituents are the same. So we have boron with fluorines, 3 fluorines here. And all substituents are the same, so you could probably guess what the polarity is going to be. And as we look at this, we know each fluorine is going to have 7 valence electrons, so 1, 2, 3, 4, 5, 6, and then the 7th, and then the shared gives it 8. So we know that each one of these is in fact happy the way it is. And boron we know has 2, 4, 6. Can only have those 6 because of its number of valence electrons that it has, and it's okay with 6. It's happy with 6. We know that this is actually going to be trigonal planar, so I'm just going to put TP for abbreviations for trigonal planar, and all substituents are the same with no lone pairs. Therefore, we know that this is actually a nonpolar molecule as well. Looking at the next examples here, we have H2O. When we look at H2O, we're going to have oxygen as our central, single bond to an H, also single bonded to another H here, with our remaining double pair on the central. This we know is going to be a bent molecule, and we know that all bent molecules are indeed polar. NH3 we know nitrogen has 5 valence electrons, so nitrogen is going to be our middle, bonded to 3 H's here. So as we look at this bonding piece here, we know that each H contributes 1 valence electron to share, leaving us with double lone pair on the single lone pair on the central. Therefore, we have a lone pair. We know that this is going to be pyramidal. And is indeed going to be a polar molecule. CO2 is one of the ones that I told you to try to memorize. CO2 we know is going to be double bonded to an oxygen, double bonded to another oxygen. No lone pairs on the central, that's what gives us our linear shape. We know that we're also going to have a double lone pair on both of those substituents because of the 6 valence electrons. So counting these, 1, 2, 3, 4, 5, 6, now 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Shape here we know is a line. We know this is linear. And for the polarity, we know that this is indeed nonpolar. Again, CL4. CL4, we know carbon is going to be our central, with 4 chlorines wrapped all the way around that. With our chlorines there, we know that chlorine has 7 valence electrons, so it just needs to pick up that extra share from the carbon. So now that it shares with the carbon, we now have 8 valence electrons in each chlorine. And our carbon is actually sharing 8 electrons altogether, so that is now sufficed filling the octet rule. The shape of this, we know we have 4 substituents, therefore the prefix tetra, therefore we have a tetrahedral. And we know that since all substituents are the same, we know that this is indeed going to be nonpolar. H2S, looking at S is actually in the same exact group as that of O, so it's going to look very similar to that of H2O. double lone pair on the S, sharing one valence electron with both of the hydrogens, therefore giving hydrogen its 2, that makes it happy, and it's sulfur giving it its 8. Substituents are not the same because of those lone pairs, and we know that this is a bent molecule, and all bent molecules are indeed polar. So we know that this is a bent molecule, and we know this is indeed polar. Last one here we have is CH3Cl. Okay, we have 4 substituents, so we know that this is going to be a tetrahedral. Based off from the tetrahedral, though, we need to look, are all substituents the same? In which we know they are not. We have 1 chlorine in here. So since our substituents are not all the same, we know indeed this is going to be a polar molecule. And again, this is a tetrahedral. One of the things that we know that comes from polarity is what's called intermolecular forces. So this is the force of attraction between the molecules. So when we look at intermolecular forces, remember this is the force of attraction between molecules. And the end result is that it influences our melting point, our boiling point, surface tension, okay, which is because of this attraction for one another. So when you think about jumping in water, when you jump into the water, you feel that initial impact because we know water is a polar molecule, therefore it has a strong intermolecular force, one of the specific types we're going to talk about in a second, and we have to break that surface tension in order to enter the water. We talk about dispersion forces, also known as London dispersion forces or van der Waals forces of attraction. When we talk about those, we know that this is actually the weakest form, okay, because it is just a temporary distortion of the electron cloud. And what that does is it's causing a shift of electrons to something that normally doesn't have a shift in electrons or polarity. And since it does that, it does it typically between 2 nonpolar molecules. One that has a higher difference between the molecules of electronegativity, therefore causing it to be temporary in which something may leave. An example for London dispersion forces is within a noble gas, or possibly in diatomic molecules as well. When we talk about dipole, remember, is between polar molecules. And that's when they're attracted to one another. Okay, as shown in the picture above here, you can see the chlorines attracted to the hydrogen. Since they're attracted to one another, there is where you'll get your dipole. Last type is a specific type of dipole that we call hydrogen bonding. It is a polar molecule involving that of hydrogen, and it is when hydrogen is bonded with nitrogen, hydrogen is bonded with oxygen, or hydrogen is bonded with fluorine. So I like to think of it as H-NOF. This is the strongest of all the types. So one of the big things that we need to talk about is table H. When we talk about vapor pressure, remember vapor pressure is when gas particles are pressing on the surface of liquid. So when we're looking at this, the big part to look at on this is when we actually look at table H. When we're looking at table H, you can see we have 4 distinct solutions here, or things I should say. So when we look at these, the ones that we need to take into consideration is which one has the most vapor pressure and which one has the least. In order to have a large increase in vapor pressure, you have to have your substance turning into a gas. So in this case, you can see which one has the steepest slope, which is that of propanone. Propanone, we know, has the most vapor pressure. Therefore, it has weak IMFs. Due to those weak IMFs, particles can spread out very easily. And since they can spread out very easily, we know that that propanone is very weak. The other one on the other end is that we have less vapor pressure. Okay, so less vapor pressure means that we have strong IMFs because those particles can't spread out as easily, turning into gas, therefore causing a lower slope. Again, you can see as I put more kinetic energy in, more average motion of my particles, these particles aren't moving around as much because they're held tightly together through their intermolecular forces. When we look at chemical reactions and types of chemical reactions, the biggest thing is being able to identify. Okay, when we look at chemical reactions, we have two larger ones that a lot of us struggle with. We have single replacement and double replacement. When we're looking at single replacement, the easiest way to determine that you have a single replacement reaction is that you're looking at a compound with a singular element. When you're looking at a double replacement, you have two different compounds switching places. So we use table J because we know that the more active element, the alone element here, we know is going to switch places or replace less active. So in this case, if you're looking at the example above, A must be more active to take the place of B. In that case, we know A is going to be a metal if it's replacing the cation, but also you could have A replacing C if they're both non-metals. When you look at table F, we use table F for telling us if we have an insoluble compound. Number one, insoluble compound must be present in order for there to be a reaction to actually take place. And remember that insoluble compound we actually call so that's our solid there, and we use table F, and we denote through table F, do we have a soluble or insoluble compound? Remember, a soluble and insoluble compound must be present in order for a reaction to take place. Or the big part there is water. The production of water would also denote that there is a reaction that has took place. Other two here we have a synthesis. Remember, A plus B producing AB, or decomp, which is AB breaking down to produce A plus B. Other part of this that we have to look at is balancing equations. So looking at equations, we want to make sure that we start and end with the most thing. The biggest part here is that we want to show the conservation of mass, energy, and charge. So when we're balancing the following reactions, the big thing that we want to look at is the difference in our elements or atoms that we have. So in this case, we have a 2 and a 3 of chlorine. So for me, if I have 2 and a 3, I'm going to look for the least common multiple. Least common multiple between 2 and 3 is 6. So if I put a coefficient of 2 there, a coefficient of 3, I now have 6 and 6. But inadvertently, I changed the quantity of my iron. Now changing that to a 2, and that 2, 3, 2 causes me to have what is now a balanced chemical expression. Looking at the next chemical expression here, again, you want to look for the biggest difference and the biggest changer. So if I'm looking at the biggest difference or the biggest changer, I'm going to be looking at what appears to be a tie. So we have a tie between PO4s, there's a difference of 1, and NO3s, which is a difference of 1 as well. And then actually there's a tie for the biggest changer, but if I actually change this quantity, I'm changing my calciums by 3. So actually if I look for my biggest changer, calcium is a quantity of 3 where it's only a quantity of 1. So my biggest change, I need to change this quantity to 3. Inadvertently now I have not just 3 NO3s but 6 NO3s, so now I must change that. So now I have 2 times 3 gives me 6 NO3s. Now I have 2 ALs. Now I must change this to 2 ALs, but now I have 2 PO4s, which is okay because I have 2 PO4s on my product side. Last one here is a little bit tricky. It's a more challenging one. Again, you're looking for the biggest difference with the biggest change. So looking at that, I have hydrogen here, and I have 2 hydrogens here, so difference of 1. I have chlorine here. I have actually a 3rd chlorine, a 4, and a 5th chlorine. My biggest thing is that when you're looking at these, we have to take into consideration what is going to cause some changes here. So we have a lot of chlorines in a lot of different places. On the reactant side, we have K, M, N, and O4. So it looks like our biggest change here is going to be in our O's. Hard part for us is that if I were to change this O's, then you're going to inadvertently be changing the H's as well. So what we need to look at is our potassiums. Potassiums, I have 1 and 1 on each side. Magnesiums, I have 1 and 1 on each side. Oxygens, I have 4, and now I have 1. So the biggest change here is going to be in our oxygens. The thing that you have to take into consideration now is if I change this by 4, that's going to give me 6, will give me 8 H's, in which then I'll be inadvertently changing these H's by 8, giving me 8 chlorines. in which I know I cannot get to 8 given 4, 4, and 1, which is an odd number. So what I want to do here, instead of putting just 4, is I want to actually multiply that by 8. By multiplying that 4 by 8, now I'm giving myself 16 hydrogens. And I'm giving myself 8 oxygens. By having 16 hydrogens, you can follow this one of two ways. You can either follow the hydrogens or follow the oxygens. I'm going to choose to follow the oxygens. So I have 8 oxygens. Easy fix for you over here is I'm going to put a 2. By putting a 2, I have now 8 oxygens, but I have also doubled my amounts of potassium and doubled my amounts of magnesium. You need to follow one or the other. I'm going to follow the chlorine, or the magnesiums. So as I follow the manganese over, I look at the manganese and I see that I have now 2 I need on this side. So as I change that to a 2, my manganese now is 2 and 2, but my chlorines are now 4, and then 5, 6, and 7. So 4, 5, 6, and 7. By changing those, the next thing I need to change to is I need to change this. By changing my potassiums, I now have 2 potassiums, okay, which also equals out this side. So now, how many chlorines do I have in general? I have 2 and 4 gives me 6, 7, 8 altogether. So looking at that 8th mark here, we need to think about our hydrogens. So looking at our hydrogens, I have 16 hydrogens here. So in order to have 16 hydrogens on this side, I'm going to multiply this by 16. Seems like a big number. So now I have 16 hydrogens. So the last part I have to fix here is my chlorines. So I have 16 chlorines. I'm already at 2, and 4 gives me 6, so I have 10. And so now I just need 10 left. So how can I get 10? From 2, multiply that by 5. By breaking it up and doing it in small pieces, it makes this a lot easier to balance. This is a much more complicated one than you'd normally see on a New York State Regents exam, but it is good for practice in balancing the expression. Next part just asks you to identify the types of reaction. This one we know is a double replacement reaction. Why? Is because we have 2 compounds forming 2 new compounds. Clearly a double replacement. This one I have 2 things joining together, so I know this is going to be a synthesis reaction. This one I have a single thing with a compound creating a new compound and a new single thing, so I know this is going to be single replacement. And the last one I have something breaking down, I know this is going to be a decomp. For each of the reactions, identify if they would occur or not. So if you're looking at this, we have to look to see if Cu is more active than that of H. And by looking at table J, you can actually see that no, Cu is not more active. Looking at the next one, I have 2 different compounds producing 2 new compounds, so we're looking at double-double replacement. So double replacement reaction, we're going to be looking at this. And if you look at table F and use table F correctly, we know that our new product of Ag, actually it'd be 2 SO4 would indeed be solid. And again, Ag is switching with the SO4. Ag has a positive 1 charge, SO4 has a negative 2 charge, so I need 2 of those, but that would indeed be a solid. Again, looking to see would the fluorine replace the chlorine, and we do know that that is going to take place because it is more active. And last but not least, we're looking at another double replacement reaction, and if you switch these, we end up with magnesium acetate, and it looks like ammonium hydroxide, and in that case, we know actually no PPT or precipitate is formed. Therefore, no reaction has indeed taken place.